Hey, Physics 30. So we are going to calculate the energy released by this uranium reaction. In this case, it's fission. You can see that I take one larger piece and it splits into two smaller pieces. So we have a form of fission here. We're really just worried about the parent particle and the daughter particles here, not necessarily these offshoot particles when we talk about fission and fusion. So we're just looking at those three to determine if it's fission or fusion. Because it looks like these are fusing together, but in terms of the larger particles being produced here, we have one big one, and we have two smaller ones. Anyway, so let's determine the mass. And down here, we got a bunch of atomic numbers. We could probably hazard a guess which one they align to based on how big the numbers are. Like the 235 number is probably going to be this guy. The 134 number, or the 140 number is probably going to be the 141. And this last one here is probably going to be the neutrons, which are going to be important in our calculation here. So the before mass, I'm just going to add all the pieces that we have before. So before we have uranium, 235. So I'm going to take that number. I'm going to add a neutron here. So 1.008664. These are atomic mass units. We'll have to deal with that later. So that's going to be my before. And my after, I'm going to add the barium, the krypton, and three of these. So that's going to be very key. There's three of those. So 140.914411. Oh, atomic mass units. Oh, it's right in there. I'm going to add a krypton. So that's a 91.926156. Sorry, atomic mass units. I'm going to add 3 times this number here together. Okay, pull out my calculator here. Got on my phone. 235.04399299. So that's the right number there. Plus 1.008664. Oops, 4. I've got a 5 there. Okay, so I got that number, which is 236.0525939 atomic mass units. And what I'm going to do is I'm going to add all these ones over here. I'm going to keep this calculator, number in my calculator here. Just put that under, store it under A there for a bit so I don't lose it. 4411 plus 91.926 plus 3 times 1.008664. I'm going to get 235. Okay, so this is a significant difference here. Atomic mass units. Okay, so the mass defect here, because it looks like I definitely lost mass here, is going to be my mass before minus my mass after. I'm not worried too much about the sign, so I'll just take the absolute value of that. And I will get a 0.186039 atomic mass units. Okay, so I'm going to quickly change that into kilograms by timesing it by the atomic mass unit number. Remember that was that 1.66 number. Let's put that over here. Times by 1.66 times 10 to the negative 27 kilograms per atomic mass unit. So that's just found on your periodic table, or not, your constant side, sorry. Cool. Okay, then I'm going to find the energy here. Easily go to MCU squared. I'm not going to show that. I'm not going to write it out, sorry. And we're going to get 2.7796 times 10 to the negative 11 joules. So yeah, really not that much when I talk about it. Like if you look at that number, that's a pretty small number. Now I said in the previous video, I was going to scale one of these up to a kilogram because this is just one nucleus. And one nucleus is really small. Its atomic mass of one nucleus in this case is 235. Actually, it just tells you right there what it is, right? So that's the one nucleus. I want to know if I had a kilogram of uranium, how much would be here? So I want to know how many of these, because that's the atomic mass of this uranium here. How many of these fit into a kilogram? So how many nuclei are there? Okay, so I'm going to find that out. I'm going to go N is equal to, I'm going to take my atomic mass number here, but I'm going to change that atomic mass number. Actually, I'm going to take the 1 kilogram first. Here's 1 kilogram. I'm going to divide it by this 235.053922 atomic mass units. Now, before I do that, I'll change this into electron-volts later. Before I do that, I got to change this atomic mass units into kilograms. So I'm just going to do that in my calculator. I'm not going to show that. Well, maybe I'll show it. Yeah. Just make sure I write the right number down. Good. Okay. It's 1.66 times 10 to the negative 27. Hey.
Good morning for you.
All right. So the mass of one nucleus of uranium times it by that number is 3.902 times 10 to the negative 25 kilograms. Here we have we're in kilograms, so I'll just leave it in kilograms. Here we have 1 kilogram. So how many can I fit into 1 kilogram? So 1 divided by this number that I have in my calculator. We can fit 2.56 times 10 to the 24 nuclei in 1 kilogram. I'll just call it particles of uranium. 235 in 1 kilogram. That's a lot of particles. And the energy that's just above there, that's the energy for 1 particle. This is just per particle, per nuclei, right? So what I'm going to do is I'm going to take those two numbers, the total energy here, so E total is going to be this number that I just found times that E up there. So I'm just going to times these two numbers together. Boop, boop. And I should have the other number in my calculator. I do, right there. So we get 7.23, or 123, sorry, 1, 2, 3, 4, that's kind of fun, times 10 to the 13 joules per kilogram of uranium 235. Okay, so the only reason I did this, because that's not what the question asked. The question asked how much energy is released by this reaction, and we found that right here. So this is the answer we're looking for, right? I can change that into electron volts. We'll just leave it in joules for now because I'm too lazy at this point. But this number times 10 to the 13 joules, even in kilograms, that's 10 to the 10 kilograms. That's a huge per kilogram. Sorry, that's a huge amount of energy. And when you think about Chem 20 and Chem 30, when you talk about thermochemistry, like a gram or a kilogram of propane, or it's only like 1,000 kilojoules or so. So not even close to this number. Uranium is way more efficient per kilogram than regular hydrocarbon combustion. Okay, remember that. Could be asked as a test question. Maybe. Okay, here's another one here. Pause the video, try this question out, see if you get this right answer. There's some numbers down here that represent those. You're gonna have to determine, because an additional neutron is used in the reaction, right? It absorbs a neutron and then neutrons are released. So you're gonna have to determine how many neutrons are actually released in this reaction by conserving the tops and the bottoms of the reaction, and then determine the energy released. And I will be back after the pause. All right, so here's my work. It's popped up in front of you. So I created the balance of reaction here. So I got uranium plus the neutron, splits into Br and La there. So La was 57, took me a little bit of time to find it on the periodic table. Yeah, BR is 35. Then I use the numbers on the top. I didn't use the numbers on the bottom because 35 and 57 add up to 92, so that worked out. The top numbers, though, if I go 87 plus 146, it's short. It's short by 3 because it's supposed to add up to 236 because I got the uranium and the neutron on one side. So I determined that there was 3 neutrons. Okay. Then I had the mass before, which I just used up here, the same numbers, uranium-235. And then a mass afterwards, I just added the pieces together, found the difference between those two numbers, changed it to kilograms, times it by C squared, got the joules. Oops, should be negative here, sorry, negative 10. Okay. Otherwise, that'd be a lot. And then I changed it to electron volts here, and I got 984 million electron volts. I just changed it to mega electron volts. And there we go. Well, that's a fun question. Okay, last question for fission here. Then we'll go on to fusion in the next video. What element has to be here? So this is, first of all, I'm missing uranium. I don't know why I never bothered fixing this. So this has got to be uranium-235. We're going to add a neutron. It's going to go to barium-144, and it's going to produce something here. Okay, so I'm just really going to look at the bottom number to determine what this is. So I'm going to go 92 minus 56. 92 minus 56. Okay, so this is just the proton, the proton count of the charge, right? So I know all the bottom numbers had to add up to 92. We got 56 plus something, plus 3 zeros, so that's why I don't have to include that. And I can determine that this is going to be 36. So I know this element is going to be 36. So I can look at my periodic table here. My 36 is going to be krypton. Kr, right? Kr, okay. Now, what version of krypton is this? What isotope is it? So we're going to look at the top numbers now. So I've got 235 plus 1. That's got to equal whatever 144 plus 3 ones, because there's 3 of those, plus this question mark. Okay? So it's got to add up to 236. So at 236, this is going to be 147 plus a question mark. That's 144 plus 3. And then I'm going to minus over the 147. And we're going to get our isotope number of 89. So this is krypton 89. I want to write that out. Let's write that out as krypton. Yeah. 89. Not just krypton, krypton 89. If you just say krypton, then I'm going to think it's krypton 84 or 83.8. So just some kind of average amount of krypton. This is very specific, krypton 89, which probably is very radioactive, and they'll continue decaying over time. Okay, so our next video, we're going to talk about fusion and how it's different than fission, and I'll see you there.